We're going to start chapter 29, covering the first couple sections. In this chapter, we're going to look at magnetic fields due to currents. Right now, previously we were looking at magnetic fields that were being sent through a wire that had a current running through it. But now we're looking at the magnetic fields that are being produced directly by these currents that are running through wires. Okay, so we're going to start with calculating the magnetic field due to a current. So the magnetic field, which we're going to call, or the magnitude of the magnetic field, we're going to call dB, so some infinitesimal element of magnetic field that's being produced by a small portion of wire at some point P away. All right, so the magnitude of this field is going to be produced at point P, a distance r, by a current length element I ds. Okay, so just looking at the picture over here, we have a wire. We're looking at some small infinitesimal element that we're going to call I, time, which is the current, times ds, which is the little bit, right, the length of the wire that is traveling through. And then we're looking at what the magnetic field produced by this current is at some point P, a distance r away. Okay, so this turns out to be this infinitesimal element dB is equal to mu naught over 4 pi times I ds sine theta divided by r squared. So this is all one equation, where theta is going to be the angle between the directions of ds, right, so basically the direction of the current, and r, which is the vector going from this element to point P. All right, r is going to be a unit vector that points from, again, ds to P, right? So this is r hat right here, just a unit vector. And mu naught is the constant. It's the permeability constant. Now, we've seen this before. It might have had different units before, but now since we're talking about magnetic fields, we need to make sure the units are aligning, make sure we're using Teslas and amps. So our unit is going to be 4 pi times 10 to the negative 7 Tesla times meters divided by amps, right? Or 1.26 times 10 to the negative 6 Tesla meters over amps. All right, so you might be wondering where this whole equation comes from. Well, this is actually was found by using experimental results. Okay, so there's not necessarily a derivation for this equation right now, but we found it by just doing experiments and figuring out the equation for that. Okay, so in vector form, this is going to look like dB, right, is going to be equal to mu naught over 4 pi, which are our constants, times the current, and then it's going to be the vectors ds crossed with our unit vector r, which just has a value of 1, divided by r squared. Okay, so this doesn't have a unit, it just has the value of 1, and it's showing us it's the angle, basically taking this sine theta and incorporating it into the cross product, right? We need to think about the angle between our unit vector r and our current, right, which is in the direction of ds. Okay. So the magnetic field due to a long straight wire. Well, the magnetic field vector at any point is going to be tangent to the circle, right? So if this is our wire of current and it's going into the page, right, you have a little X there. If the wire is going into the page, the magnetic field is just going to be, the magnetic field lines are going to be circular all the way around. So the direction of the magnetic field is just going to be tangent to any of these circles. The magnitude of the magnetic field at a perpendicular distance r from a long, infinite, straight wire carry a current I. And that's going to be given by B is equal to mu naught I over 2 pi r. All right, so this is going to be for a long, straight wire. All right, and we're going to use the equation we found earlier to solve for this in a second. We'll look at what the derivation looks like. But before that, I just want to look at, so the iron filings have been sprinkled onto a cardboard collect in concentric circles when current is run through this central wire that kind of goes down through the middle here. And the alignment, which is along the magnetic field lines, is caused by the magnetic field produced by the current. Right? So basically, these little iron filings are going to be sort of induced to have this magnetic dipole being produced in them, where you have a north and south pole, and they're going to line up along the magnetic field lines. Real quickly, I wanted to go back to this equation and say that this is actually something called the Biot-Savart law. Right? And this is basically the central equation that we're going to be using when we're trying to find what the magnetic field due to a current is. Right? And this is sort of, they say in the book, it rhymes with Leo Bizarre. Right? It rhymes with that. So it's Biot-Savart is how you pronounce that. Okay. All right, so let's keep going. So the right-hand rule, when you think about, well, the direction of the current and the direction of the magnetic field, so the right-hand rule says you're going to grasp the element in your right hand with your extended thumb pointing in the direction of the current. Right? So if you have a wire, you wrap your hand around it, as shown in this first picture here, and you want to point your thumb towards the direction of the current. Your fingers will then naturally curl around in the direction of the magnetic field lines due to that element, right? So if you're looking at this one, if the current is going down, since our fingers are kind of curling around towards the backside, we say that the current is going into the page here and out of the page over here. And then opposite for the opposite case. So if the current is going up, your thumb would be pointing up. You're curling your fingers around, so it's going to be going into the page here and out of the page over here. Okay. All right, so let's look at the magnetic field due to a long straight wire and what the derivation of that would look like. Well, we're going to start with the form of the Biot-Savart law that has the sign in it, the sine theta. All right, so we say that dB is equal to mu naught over 4 pi times our current ds sine theta, which is the angle between, again, the unit vector r and the ds, and then divide by r squared. All right, well, if we take the integral of that, we can get the total amount of magnetic field is equal to 2 times the integral of dB. Now we have a 2 here because if we look at our picture, all right, so we're talking about some infinitesimal element over here. Let's say that's our element over there. We know that the r vector is pointing towards P, which is down here. We know that's going to cause a magnetic field into the page if the current is going up at this point. The ds element is going to be going along with the current, so that's going up, so our theta is going to be that angle between them. Now, this would really only account, right, the integral from, let's say, 0, which is going to be here, all the way to infinity, is only going to account for half of the magnetic field that's being produced at point P. So we need to think about the other half, right, going down in this direction. And it happens that the magnetic field over here is going to add. So this element down here is just going to add in the same direction as the top half. So we can just multiply this integral from 0 to infinity by 2. Okay, so we do that, and that's going to be equal to mu naught I. We're pulling out our constant, so we're going to pull out the I, which is the current. That doesn't change. And then now we have only 2 pi on the bottom, right, because we have a 2 here, and that's going to cancel out with a 4 there. So we're left with 2 at the bottom, the integral from 0 to infinity, and then all we have left is going to be sine theta ds divided by r squared. Okay? Well, we know a couple things. We have multiple variables here, but we can see that they are actually all related to one another. So if we look at our r, which is, again, this distance here, we can see that that's actually related to s, and it's related to the radius, right, the distance directly away from the wire. So we can just write that as r is equal to the square root of s squared plus r squared, which is the two sides of the triangle. Now also we can look at this sine theta term here, and we can relate that sine theta to, that would be the same thing as the sine of pi minus theta. Right, so this is theta, right, but it's also the same thing as this angle right here, which is pi minus theta, right, because this whole thing is pi minus theta is going to give us that angle right there. All right, so that is going to equal the theta of this triangle. And since we know that the sine is opposite over hypotenuse, we can just go ahead and say that that's going to be equal to r divided by our hypotenuse, which we just found here, which is our square root of s squared plus r squared. Okay, so now that we figured out another way of writing sine theta, and we figured out another way of writing r, we can plug both of these two things back into our original equation. So what we end up with is the magnetic field is equal to mu naught I divided by 2 pi times the integral from 0 to infinity of r ds, right, because we took that r comes from right here. We're replacing sine theta with this, divided by what we have left on the bottom is going to be s squared plus r squared to the 3 over 2. Right, because if we have this r squared here, we plug in this for r, right? So this basically leaves us with s squared plus r squared. Right, so basically it's this value to the 1, or to the 2 over 2. And then we're adding an additional 1/2 to that. So we're going to get 3 over 2. Right, 3/2. Alright, so that's where we get our exponent there. Alright, now we can go ahead and, take the integral. So at this point, our s is the variable, our r is a constant. You can get the r out of there. It's actually going to cancel out once we do this integral. You can go to your table of integrals and figure out that the solution to this is going to be mu naught I 2 pi r. Right, we put out an r, then an r comes out of here too. And then we get s divided by s squared plus r squared to the 1/2. And our limits are going to be 0 to infinity. Okay, so looking at what we have inside of what we have our limits for, we know at 0, this whole thing is going to be 0, right? Because if you plug in 0 for s, this whole term is 0. At infinity, you have s on the top, and you have s squared, but you have it square rooted, and this constant has no effect on the equation. That's just going to disappear as when you go to infinity. So you have s squared to the square root. So really you have s over s, which is 1. All right, so now you have 1 minus 0, which is 1. So really all you're left with is that. Oops. All right, so this is simply going to be mu naught I over 2 pi r. That is equal to our magnetic field. This is for an infinite straight wire. What if you had only half of it? Maybe you had a long piece of wire that ended like right here and went upwards. None of this was there. It would just simply be 1/2 of that. Right? So if that was 1/2, then our magnetic field is going to be mu naught I divided by 4 pi r. This is going to be for a semi-infinite wire. Okay, and let me stress, this should also be a straight wire. I'm talking about straight wires here. Okay. All right, so now what if we had a curved wire? All right, well, we can look at the derivation for that. It's a little simpler. We're going to start with the equation we did last time. So our dB is going to be mu naught over 4 pi times the current ds sine theta divided by r squared. All right, so let's look at our setup here. You have some piece of wire that has an angle of phi. The radius is going to be r. You have a current running through it. When you're going around a circle, you know that the angle between your ds and your current element is going to be always going to be 90 degrees to your unit vector r. So since it's always 90 degrees, this term here, which is sine 90, is going to be 1. All right, so basically your sine term goes away. All you're left with is mu naught over 4 pi times I ds over r squared. All right. So now we want to find what the total magnetic field contribution is, since this was only part of it. All right, so we're going to go and take the integral of dB. And our limits are going to be from 0 to phi. Right, because we're going from this point all the way through to that point, so that'll be our limit. So we get mu naught over 4 pi times the current times r times phi. Okay, so it's I times this ds element, and this ds element is actually our circumference of the circle. Our circumference is simply going to be the radius times that times the angle, right? Times that angle traveled. All right, so that's why we have I times r. This is going to be our ds element right there. And we divide by r squared. Okay. Now, this actually simplifies quite a bit because I is a constant, r is a constant, and then again, r is a constant. So really all we have as a variable is this phi. All right, so our magnetic field is then going to be mu naught I 4 pi r times the integral from 0 to phi of d phi. All right, which we know is just going to be phi. So B is going to be mu naught I times phi divided by 4 pi r. All right, so this is going to be the magnetic field at the center of a circular arc. Okay. Well, what if I wanted the magnetic field of a full circle, right? A full loop of current. Well, that's simply going to be mu naught I times 2 pi, because our phi is going to be 2 pi, right? Full circle. 4 pi over r. So that's simply mu naught I divided by 2r. And this is going to be at center of full circle. Okay. All right, let's do an example. All right, so looking at this, it looks kind of complicated, all right, but if you break it down, it's really not that bad. So in the wire, the wire carries a current I and consists of a circular arc of radius r and a central angle of pi over 2 radians, and 2 straight sections whose extensions intersect the center C of the arc. What magnitude field B, magnitude and direction, does the current produce at C? Okay, well, let's first look at each section at a time. So we're going to start with sections 1 and 2. So for any current length element in section 1, the angle between ds and r is going to be 0, right? R is going to be in this direction, and our current is also in this direction. Right? That's going to be our ds. They're both going in the same direction, which means that, so dB1 is equal to, using our equation, for a straight line, it's going to be I ds sine theta. Actually, we're just going to use Biot-Savart law here. All right, so this is mu naught over 4 pi I ds sine of 0 divided by r squared. Sine of 0 is 0, so our contribution here is 0. Right? So this current does not provide any magnetic field at point C. Now, the same situation is going to happen in the second wire, right? So B1 is going to be 0. The same situation is going to happen in the second wire, right? Except your angle is 180, and the sine of 180 is also 0. Right? So our B2 is going to be 0. All right, so now let's look at the circular arc. So we're going to use, didn't realize we were off the page there. All right, we're back on track. So we're going to use the Biot-Savart law to evaluate the magnetic field at the center of this circular arc, right? And we know that that leads to our equation we found in the previous slide, that B is equal to mu naught I phi over 4 pi r. And in our case, we know that our angle phi is just pi over 2, so you get mu naught I pi over 2 divided by 4 pi r. And that's simply going to be mu naught I divided by 8r. Okay. So to find the direction of B3, we apply the right-hand rule, and we mentally grasp the circular arc with our right hand. So we're taking this arc and we're wrapping our hand around it. But your thumb needs to be in the direction of the current. So when we do that, we sort of have to kind of wrap our hand around the other way. Right? And we can see that when we do that, at point C, the fingertips are going to point into the plane. All right, so if we wrap it around, we end up getting our finger points pointing into the plane right there at point C. All right, so now we know the direction of our magnetic field at that point. All right, so generally, when we must combine two or more magnetic fields, to find the net magnetic field, we must combine the fields as vectors and not simply add their magnitudes. Here, however, only the circular arc produces a magnetic field, thus we can write the magnitude of the net field B as simply, so let's see, B is going to be B1 plus B2 plus B3, which is 0 plus 0 plus mu naught I over 8r. And we say that's equal to simply mu naught I over 8r. Right, so this is what our total magnetic field is. Oops. Total magnetic field is at that point in time. Oop, I moved it over again. All right, but that's the end of the lecture, so we'll see you next time.